Planet Earth. 4.5 billion years old. A solid ball of rock weighing 6 trillion tons. We are on a quest to destroy it. Using cutting-edge physics and planetary science, we will explore what could destroy our planet completely. A black hole?
It might seem harmless, but its gravity is strong enough to destroy the entire planet Earth.
A collision with the sun?
And before you know it, the Earth is falling into a fiery plummet.
A huge antimatter bomb?
Poof, okay, at a huge annihilation.
A giant rock from space?
You wouldn't want to be standing here 50,000 years ago.
Or perhaps a swarm of self-replicating robots.
It's been a nightmare of sci-fi.
These ideas may sound like science fiction, but they're all grounded in proven scientific fact. Our planet is seriously tough. It has survived everything a hostile universe could throw at it for 4.5 billion years. Yet in the past few decades, we have developed technologies so powerful that some people fear we could literally destroy the Earth. It's time to find out if they're right. 6 top scientists are about to reveal what it would really take to destroy an entire planet. Our first candidate is a black hole, the greatest destructive force in the universe. A black hole is what's left when a giant star collapses in on itself. The result? Gravity so strong that nothing can escape, not even light. Soon, we may be able to create black holes right here on Earth. Physicists use huge particle accelerators to try to recreate what happened after the Big Bang. But when they smash particles together, they also risk creating a black hole. Think of a black hole as Niagara Falls, and the water going over like space getting sucked in. This unfortunate kayaker has gotten too close. Just like a star getting too close to a black hole. Dr. Phil Plait, astronomer and author.
The water going over the lip of the waterfall is just like space itself falling into a black hole. If you're kayaking, no matter how fast you paddle, once you go over that lip, you're going down. That's the point of no return. And it's the same thing with a black hole. No matter how fast you try to get out, it's going to take you down.
The gravity in a black hole is fundamentally different from the gravity we experience in normal life. Normal gravity you can escape from, at least in theory. Cosmologist and golfer Professor Lawrence Krauss.
It's commonly said that what goes up must come down, but that's not always the case. For example, if I hit this golf ball here and I hit it well, it would go fairly far, but it would still come back down to Earth. If I hit it harder, it would go further and still come back down. But if I hit it with a speed of 5 miles per second, it would escape from the Earth's gravitational field.
But for the ball to escape from a black hole, it would have to move faster than the speed of light, and that is simply not possible. What goes into a black hole, planets, or even stars, never comes out. Our small planet wouldn't stand a chance. For anyone looking for a way to destroy the Earth, black holes are a good place to start. The trouble is, there are none close by enough to do the job. Unless we make one. That's where the atom smashers come in. With a lot of math and a gigantic machine, physicists can now generate atom-sized explosions that may be powerful enough to create microscopic black holes. They are trying to study the Big Bang. The force of the impacts recreates the particles that made up the universe in its earliest moments. Some of those particles may create microscopic black holes. That doesn't mean our planet is doomed. In theory, black holes this small would just evaporate like tiny soap bubbles. To destroy this, you need something bigger.
Black holes come in all sorts of different sizes. For example, at the center of our galaxy, there's a black hole of 1 million solar masses. If you took the mass of our sun and compressed it down to be a black hole, it would be the size of a large American city like Phoenix here. On the other hand, if you took something like this mountain here, which is maybe 1 million tons, and made it a black hole, it would be smaller than the size of a single atomic nucleus.
Somewhere along that scale, black holes get powerful enough to cause serious damage. To destroy the Earth, it turns out you need a black hole that weighs about the same as the Earth. The Earth is 8,000 miles across. But a black hole weighing that much would be the size of a marble. Professor Clifford Johnson, physicist.
Here I have a marble-sized black hole. It might seem harmless, but its gravity is strong enough to destroy the entire planet Earth. What would eventually happen is that it'll start sucking things in, slowly at first, and then it will grow in size. It will grow and grow and grow until it swallows the whole Earth.
To imagine what that marble would do to the Earth, picture what it does to a physicist.
The gravity is much stronger on one side of an object closer to the black hole than it is on the other side of an object, producing an effect that's called spaghettification, as that object is stretched out and pulled apart as it falls into the black hole.
A big enough black hole could do this to our whole planet. There's no way even the most powerful atom smasher could make a black hole this big. To destroy the Earth, we need to find one ready-made. Astronomers think there are 10 million or so black holes in our galaxy. If one of them strayed into our neighborhood, it could rip our planet to pieces. Earthbound telescopes may not even detect it. Humans would only know it was approaching when its immense gravity triggers huge floods and earthquakes. As it plunges into our atmosphere, the black hole acts like a vacuum cleaner, sucking with a force over 1,500 times Earth's gravity. Then it begins to distort the shape of the whole planet. Earth's surface stretches and tears apart. Finally, the hole hits and flies straight on in, heating and vaporizing matter as it goes. It starts to orbit the Earth, inside the planet itself, all the time devouring everything in its path. Gradually, the orbit slows. The black hole spirals down into the Earth's core. Eventually, it eats the entire planet. All that's left is the black hole itself. It's a devastating end for planet Earth. But fortunately for us, it's unlikely ever to happen.
If you want to destroy a planet, a black hole is a great way to do it. But the problem is, it depends on the kind of black hole. A microscopic black hole would just pass right through the Earth, and it really wouldn't do that much damage. A black hole with the mass of the Earth would be about the size of a marble, and that would do a considerable amount of damage passing through the Earth. But again, it might not destroy the planet. If you want to do the job right, you need a stellar mass black hole, something with about 3 times the mass of the Sun. That thing would come in and it would tear the Earth apart and gobble down the pieces, and it would be game over. The problem is, we don't know how to make any of these black holes. Technologically, we just can't do it. And with a naturally existing one, we don't know how to move them. So there's got to be a better way.
So if black holes don't work, time for a new approach. One surefire way to destroy the Earth is to change its distance from the Sun. Move the planet closer and it bakes. Move it out and we freeze, sending us into another ice age. Scientists have recently begun to realize that moving a whole planet might actually be possible. In fact, we use the same principle to slingshot space probes round the solar system. Planet Earth could be just a few well-placed flybys away from a fiery death. What would it take to incinerate an entire planet? Answer: a nuclear furnace nearly 1 million miles across. It sounds crazy, but the truth is this will happen. It's just a matter of time.
As the sun gets older and older, it's going to actually get brighter and brighter. And within about 2 billion years, the Earth will be in an uninhabitable zone. It'll be like Venus. There'll be a runaway greenhouse effect. All the water on Earth will be destroyed, and the surface temperature will be about 1,000 degrees.
Eventually, the sun will swell and scorch the Earth, unless we somehow move the Earth away from the sun to save it.
Alternatively, if you were sufficiently evil, I suppose, you could imagine doing exactly the opposite. Harnessing sufficiently large objects to transfer gravitational energy to kick the Earth's orbit closer to the sun.
Easy to say, not so easy to do. The Earth weighs in at 6 trillion tons. Pushing something that big is quite a challenge. But there is a way. It's called gravity assist. Space probe engineers use gravity assists all the time. Take Saturn's Cassini-Huygens probe. It's the size of a school bus, one of the biggest probes ever built. To build up enough speed to fling the probe out to Saturn, it had to swing by Venus twice and Earth once. Each flyby stole energy from the planet and added it to the probe. The probe got a lot faster by altering the planet's course just a little.
The name of the game, we take a rock about 1 mile or 2 across, and we move it so that it just passes the Earth the right way, and it'll steal energy away from the Earth. The asteroid will go flying off, and the Earth will move in toward the sun. But we shouldn't just waste the asteroid when we can recycle it. If we're clever, we can take the asteroid and have it go toward the planet Jupiter. And then if we pass Jupiter in just the right way, it'll take that extra energy it stole from the Earth, give it to Jupiter, and then fall back toward the Earth. And if we aim everything just right, we get a conveyor belt of energy. We steal it from the Earth, give it to Jupiter, and then come right back. And in fact, we can use hundreds or even thousands of asteroids this way, continuously stealing Earth's energy and dumping it toward Jupiter. And before you know it, the Earth is falling into a fiery plummet.
First, you need to catch an asteroid. It's as big as a mountain, and it's traveling around 10 miles a second. Next, you need to attach rockets and boost the asteroid onto the perfect course. Next, repeat, thousands and thousands of times. Very slowly, over thousands of years, the Earth will fall towards the Sun. Right now, we're just over 90 million miles away. By 70 million, the Earth is a superheated desert like Venus. Then things start to get really bad.
As the Earth slowly spirals into the Sun, a series of events unfolds which unfortunately spells doom for our planet. As the Earth approaches the Sun, the atmosphere heats up and blows off, and the oceans boil, basically turning the Earth into a giant comet. But there's worse to come. As the Earth gets closer to the Sun's gravity pulls on the near side of the Earth more than it pulls on the far side, and the Earth stretches like putty. At some point, it gets close enough to the Sun that the Sun's gravity can overwhelm the Earth's gravity, and it shatters, pulverizes our planet.
The Earth is dead, but its ghost could remain, a faint ring of material around the Sun. Peter Schultz, planetary impact geologist.
If the Earth or any object gets too close to another object like the Sun, eventually the tides will rip it apart. As that happens, it would simply be broken into many small pieces that would then encircle the Sun as if it were a ring.
The Sun would resemble Saturn, with its own faint ring of rocks and dust. A fiery death and a ghostly remnant. If you want to destroy a planet, this could be the way to go.
A great way to destroy the Earth is to drop it into the Sun, let it plummet to a fiery death. And we can do this. All you need to do is to pass enough asteroids near the Earth in succession to gravitationally drop it into the Sun. And we have that technology. We know how to move asteroids. It's just a matter of getting them on a precise enough orbit to be able to do it.
Maneuvering billion-ton chunks of rock with pinpoint precision at hundreds of miles a minute is quite a stretch. Not to mention the amount of time it would take to capture enough asteroids. We've tried to crush it and burn it. It's time for another plan. An antimatter bomb. Physicists have been searching for over a century for a theory that unites our understanding of the large-scale universe, planets, galaxies, and stars, with what we know of the subatomic world, electrons, protons, and quarks. Their theories are bringing to light some pretty destructive phenomena. One of them could be a world killer. Antimatter. Theorized in the 1920s, detected in the 30s. Now we can create antimatter in modern particle colliders. And the base ingredient for the biggest explosion possible. Antimatter is the most explosive substance ever found. Pound for pound, it's far more powerful than even a hydrogen bomb. But antimatter is hard stuff to find. Everything we see around us, out to the most distant galaxies, is matter, created 13 billion years ago in the Big Bang. It created antimatter too. They look similar. In fact, they are entirely opposite. Put them together, and they wipe each other out. Cosmologist Lawrence Krauss.
Now I have a proton here, and anti-Krauss over there has an antiproton. And when we bring them together, we're going to make an incredible explosion. Okay, let's annihilate.
This is what happened to all the antimatter created in the Big Bang. It annihilated. If we want to use some for a bomb, we need to make it ourselves. Making antimatter is a bit like firing a gun at a target.
If I shoot a gun at a paper target, the paper that flies out of the target is like matter, and the hole that's left behind is the antimatter. It takes energy to create a matter-antimatter particle pair. In the shooting range analogy, the bullet provided the energy.
In reality, the gun is a particle accelerator, like the one at CERN in Switzerland. Fire protons in a giant tube, steer them around with powerful magnets, use the same magnets to accelerate the protons to near the speed of light, then slam the beam into a block of metal. For every million protons that hit, you get one antiproton. It's as if Plate's handgun only left a hole once in every million shots.
In an accelerator, you only get one particle-antiparticle pair out of every million collisions or so. And so it's really hard to find that one antimatter particle floating around. It's a lot like coming to Niagara Falls and trying to get that one particle out of all the mist. And that's why it's so hard to create antimatter on a large scale.
Assuming we can obtain enough antimatter, the next challenge is to make it into a bomb. Nothing is more unstable than an antimatter bomb. You have to find a way to hold the antimatter without it touching any ordinary matter. If it does, it will explode.
So I have a bunch of antimatter above my hand here. Well, it better not touch my hand, because if it does, poof, okay, at a huge annihilation. But worse, it can't interact with the air around it, because the air is made of matter. And again, you'd get an incredible explosion.
Researchers need a special container to study antimatter. And this is it, a penning trap. Powerful magnets suspend the antimatter in a vacuum.
So if I want to store this antimatter, what I have to do is somehow keep it levitated above my hand, which means I'd have to produce huge magnetic fields in just the right way to keep the charged particles in the antimatter from touching my hand. But I'd also have to store it in an incredibly high vacuum, because any air in the container would again cause an explosion. And so the energies and technology required to produce those magnetic fields, keep that ultra-high vacuum, would mean that you wouldn't have a small object. You'd have to have surrounded with massive amounts of machinery.
Yet, for all that trouble, an antimatter bomb isn't just theory. We can make antimatter, we can capture it, and we can store it. But where do we plant it for maximum effect? If we want to destroy the whole planet, the bomb has to go off near the Earth's core. That's nearly 4,000 miles straight down, further away than London from DC. Right now, that's impossible. The deepest man-made borehole stops at just 7.5 miles. But what if we could? So far, mankind has managed to create a grand total of 20 nanograms of antimatter. That's 100 million times lighter than a dime in your pocket. So the bomb is going to be too small even to see.
Well, 200 feet away in this test range in Arizona, we have the explosive equivalent of TNT. So let's see how big of a bang that makes. Wow.
20 nanograms of antimatter makes quite a blast, but it's way short. To destroy planet Earth, we would need 2.5 trillion tons of the stuff. That's a bomb the size of Mount Everest, at the bottom of a hole 4,000 miles deep. If it were possible, the result would split the Earth into thousands of pieces. With a powerful enough bomb, the pieces would fly out into space and are lost. With a slightly weaker bomb, the pieces fall back under the force of their own gravity, collapsing into a molten ball. An eerie echo of Earth's creation 4.5 billion years ago. It could happen, in theory, but there are a few technical details to iron out first.
So what's the matter with antimatter? Well, if you're trying to destroy the Earth, it'll work, it'll do the job. The problem is you need about the energy that the sun puts out in an entire week. So it's a huge amount, and we just don't have the technology to create that right now.
At the present rate of production, making the bomb would take more than the age of the universe.
The other problem is getting it to the Earth. How do you do that? Well, you'd have to get it to the center of the Earth, and that means digging a hole several miles across and 4,000 miles deep. So in the end, don't think antimatter is probably the most efficient way of destroying the planet.
So, as a way of destroying the Earth, maybe antimatter has some problems. But we know the next approach works, because it already happened once before in Earth's ancient past. Space is a dangerous place. It's full of debris. Rocks the size of pebbles, up to rocks near the size of a planet. There are impact craters everywhere, including our moon. These asteroids can hit us as well. An asteroid wiped out the dinosaurs. Maybe a bigger asteroid could destroy the planet entirely. Meteor Crater, Arizona. Almost a mile across, nearly 600 feet deep. Today, science can reconstruct what happened here thousands of years ago. Dr. Dan Durda, planetary scientist.
You wouldn't want to be standing here 50,000 years ago. This iron meteorite, about the size of a small office building or so, it's made out of stainless steel from space. It's about to strike the desert with an impact energy of somewhere between 1 and 10 megatons. And it's that energy that's going to excavate and open up this crater behind me, which is nearly a mile across.
The impact ultimately devastated an area the size of New York City, with 600 times the power of the Hiroshima bomb. And that was small. 65 million years ago, a real monster struck. It was 6 miles across. Sat on the ground, it would outtop Everest by half a mile. The crater was over 100 miles wide. The impact wiped out the dinosaurs and destroyed most of life on Earth. An even bigger space rock could destroy the planet. We're already developing technologies to protect against future impacts. Ironically, you could use those same technologies to make an impact happen. One approach is to hover a space probe near the asteroid. The probe's mass generates a tiny gravitational pull on the rock. Over time, that can change the asteroid's course enough to miss the Earth, or to guarantee a hit. Another protection technology that we could use is a technique called solar sublimation. This diverts an asteroid or comet using nothing more than sunlight. To demonstrate the effect, Dirda starts by building a homemade comet.
Some fraction of near-Earth objects are comets, so let's examine what comets are made of. Let's actually make a comet.
Take some soil, add dry ice, then water, and some chocolate.
We'll put in a few percent of organic material into our comet. And of course, in the outermost solar system, there's a little bit of ammonia here and there. We'll let that be represented by this ammonia cleaner. Let's see if we can pack this up and make ourselves a little comet nucleus.
A magnifying lens completes the apparatus.
If one were to actually focus the light from the sun onto the surface, one could cause some of that water to vaporize away. And just like on this comet nucleus, the jetting action of those evaporating gases act a little bit like little artificial rocket motors attached to the object. And over time, they really do cause it to be pushed slightly off course.
The power of sunlight alone is enough to divert a space rock onto a collision course with Earth. But solar sublimation may not be effective on an object big enough to pulverize our planet. To destroy the Earth, our space missile needs to be big. Like Mars big. We know this for certain because it's happened before. 4.5 billion years ago, a rock the size of Mars struck the Earth a glancing blow. The impact debris created the Moon. If it had hit head-on, none of us would be here. We've come here to the vertical gun range at NASA Ames in California for proof. This 12-foot gun fires beads up to 4 miles per second, 6 times faster than a rifle bullet. Professor Peter Schultz, a planetary impact geologist, uses the gun to simulate a Mars-sized object, represented by this small projectile, hitting our planet head-on. The Space Environment Chamber is ready. Schultz makes his final adjustments. But will our scale model Earth break apart completely?
That hurt. That really hurt. Look at this thing, this is worse than a science fiction movie. That's just glorious disaster. There's nothing left.
A head-on strike, destruction guaranteed.
So the things that destroy an object is going to be a combination of the size of the object, the speed of the object, and the angle. The lower the angle, the less likely it'll completely bust it apart. So to really destroy the Earth, you need something that's humongous and needs to hit straight on.
Now we know what it takes to use an impact to destroy planet Earth. Asteroids and comets are just too small. We need to move something the size of a planet onto a collision course. That's a level of technology we won't be reaching anytime soon.
Now, we can move asteroids around and we can move comets around, but those are only a few miles across. The problem here is that we need something really big. Mars is about a third of the size of the Earth, and even that hitting the Earth won't destroy it. We would need something almost as big as the Earth itself, something like Venus. And even then, we just don't have the technology to be able to move something that big with that kind of precision to aim it at the Earth and blow it up.
Destroying the Earth with a space rock just isn't gonna happen. Perhaps the killer punch won't come from space, but from right here on Earth. Genetics, robotics, nanotechnology. Researchers hope machines will lead us to a brave new world. Already, robots can learn, build other robots, and cooperate with each other. It could be the beginning of a new age. It could also be the beginning of the end. Right now, we can only build robots that work with humans in control, but science is working towards machines that can think for themselves and even reproduce. Robots that can make copies of themselves without human control could one day take over the world. Hod Lipson, professor of robotics. Lipson is a pioneer in robot replication.
If this robot could make another robot identical to itself, and then those two robots can make 4 robots and so forth, these robots could fill up a space such as this here fairly quickly.
Once the first replicate is made, there's no stopping the process. But first, we've got to make them. At Cornell's robotics lab, Lipson and his team already make robots that learn, robots that build, and robots that build themselves. This is the world's first self-replicating robot. Supply it with building blocks and it assembles them to make a copy of itself. It needs Lipson and his lab techs to keep it stocked with plastic cubes. So this robot is pretty benign. To destroy the Earth, we need to develop robots that use smaller blocks and eventually individual atoms.
We've been trying to make robots made of much tinier cubes on the order of 0.5 millimeter, and you can barely see them. There's about 10 of them in this container here. We're trying to get these very small units to combine together, and the smaller they get, the faster and more easy it is to replicate.
Lipson thinks that advances in robotics will revolutionize design and manufacture. But where there's progress, there's also danger. In theory, nano-sized machines could start to replicate out of control. Self-replicating nanomachines could, in theory, destroy all life on Earth. To destroy the planet itself, we need something more. To reproduce, a robot needs energy and raw materials. In other words, food. The more food there is, the more copies our robots can make. And the biggest source of food on the planet is the planet itself.
The ultimate kind of self-replicating process is something that's inspired by nature. So if we can have a machine that can essentially self-replicate using resources in the environment, food and energy, then that would be a pretty big achievement.
And the biggest natural resource on Earth is rock. Design a self-replicating robot that feeds on rock, and it has 6 trillion tons of food right under its feet. Some living creatures already use rock. Rock-feeding bacteria live in the Earth's crust, even several miles deep. But nature's rock eaters are good for the planet. They help form soil and keep life ticking.
There's a whole suite of rock-eating bacteria that we've now uncovered on the Earth, which will go and chew up and eat and use the materials in the rocks for their sources of energy and for the sources of compounds they use to build other biologic molecules. There are literally biologic organisms that do just this, eat rock.
Rock-eating, self-replicating robots. But they've got to be smart. They need to cooperate. Professor Alan Winfield, roboticist in charge of the Symbrian project, to design robots that swarm like insects.
Symbrian is a 5-year project to try and build a swarm of self-assembling robots. Perhaps as many as 30 or 40 will physically join and then behave and act as a single organism. The big challenge is going to be how to get the robots to first of all decide what to be: a foot bot, or a knee bot, or a sensor bot, or a brain bot, and then work cooperatively so that, for instance, the organism can stand up and walk.
We can already make robots that reproduce. We can make robots that cooperate. Put them together, and at last we may have our planet killer. Here's the math. Say each robot takes 1 day to replicate. Then after a single month, you have over 1 billion robots. After a year, you have trillions. Earth is covered with machines that do nothing but gobble rock. In the end, no more rock, just a huge ball of self-replicating machines.
Now, what are robots made of? Well, iron, magnesium, aluminum, and silicon. The same thing the Earth is made of. And so all you have to do is create one of these self-replicating robots and let it out into the wild. It'll make a zillion copies of itself, and they will consume the Earth, and eventually there'll be nothing left.
Success at last? Perhaps not. In our quest to destroy the planet, we've tried devouring it, incinerating it, pulverizing it, blowing it up, and breaking it down. Planet Earth is a proven survivor. It has taken everything the universe can throw at it for 4.5 billion years. And one thing is certain: we're still here.